When NASA's computers started receiving impossible data from the edge of our solar system, scientists couldn't believe what they were seeing. After 47 years of silent travel through the cosmic void, Voyager 1 has transmitted discoveries that challenge everything we thought we knew about interstellar space. Today, on Sci and Why, we're unveiling the shocking revelations that have left astronomers questioning the very nature of our universe. From mysterious humming sounds to unexplained cosmic phenomena, these findings will change how we view our place in the galaxy forever. The impossible mission that defied all odds. Voyager 1 was designed to last just 5 years, yet it's still transmitting data after nearly half a century, making it humanity's most successful space mission ever. In 1977, NASA launched what seemed like a routine planetary exploration mission. Voyager 1 and its twin, Voyager 2, were built using 1970s technology with computer systems containing just 70 kilobytes of memory, less than a single smartphone photo today. Originally designed to study Jupiter and Saturn during a rare planetary alignment, these spacecraft were expected to go silent by 1982. Instead, they embarked on humanity's greatest journey into the unknown. The mission capitalized on a once-in-176-year gravitational alignment that allowed the spacecraft to use planetary gravity as cosmic slingshots, accelerating them toward the outer solar system. What began as a 5-year mission has become a 47-year odyssey that redefined our understanding of space. Today, Voyager 1 travels at 38,000 miles per hour through interstellar space, sending back data from regions no human-made object has ever explored. The fact that this 1970s technology continues functioning in the harsh environment of deep space represents one of engineering's greatest triumphs. Crossing the final frontier into interstellar space. On August 25, 2012, Voyager 1 became the first human-made object to leave our solar system, entering a realm where the sun's influence ends and true interstellar space begins. The moment Voyager 1 crossed the heliopause, the boundary between our solar system and interstellar space, marked a historic milestone for humanity. At 11 billion miles from the sun, the spacecraft detected a dramatic change in its environment. The solar wind, a stream of charged particles flowing from our star, suddenly dropped to nearly zero, while cosmic radiation increased threefold. This transition wasn't gradual, it was like stepping from a protected harbor into an open ocean. The heliopause acts as our solar system's shield, protecting us from the galaxy's intense radiation. Beyond this boundary lies the interstellar medium, a vast expanse filled with remnants from ancient star explosions, cosmic dust, and mysterious phenomena that scientists are only beginning to understand. Voyager 1's instruments detected strange magnetic field fluctuations and unexpected particle densities that contradicted existing models. The spacecraft found itself in an environment where the familiar rules of our solar system no longer applied. This crossing represented more than a technical achievement. It was humanity's first step into the galactic neighborhood, opening a new chapter in space exploration. The mysterious humming sound from the void. Voyager 1 detected a low, persistent humming sound in the supposed silence of interstellar space, a discovery that has scientists completely baffled about what's creating this cosmic symphony. In the vacuum of space, sound shouldn't exist. Yet Voyager 1's instruments detected something extraordinary, a continuous, low-frequency humming emanating from the interstellar medium itself. This wasn't sound as we understand it on Earth, but rather vibrations in the sparse gas and plasma that fills the space between stars. The humming appears to be generated by the interstellar medium's interaction with cosmic phenomena, creating a kind of cosmic background music that permeates our galaxy. Scientists describe it as similar to the sound of wind through trees, but occurring in a medium millions of times thinner than Earth's atmosphere. The discovery challenges our understanding of how energy propagates through space, and suggests that interstellar space is far more active than previously thought. These vibrations might be caused by stellar winds from distant stars, shockwaves from supernovae, or even more exotic phenomena we haven't yet identified. The humming varies in intensity and frequency, suggesting it responds to changes in the local interstellar environment. This cosmic soundtrack provides scientists with a new way to study the structure and dynamics of our galaxy, turning Voyager 1 into an interstellar seismograph. The heliopause's shocking behavior. You know, the boundary of our solar system isn't the stable barrier scientists expected. Instead, it's moving, shifting, and behaving in ways that completely contradict our models of how space works. The heliopause, which is our solar system's protective boundary, has revealed itself to be way more dynamic and unpredictable than anyone imagined. Rather than maintaining a steady position, this cosmic border actually fluctuates dramatically, sometimes moving billions of miles in relatively short periods. Data from Voyager 1 and 2 shows the heliopause exhibiting strange angles and irregular shapes that just defy current theoretical models. Back in 2014, NASA's Interstellar Boundary Explorer satellite detected unusual brightening of energetic particles, which suggested massive disturbances in the boundary region. These irregularities simply don't match existing predictions about how the solar wind should interact with interstellar space. The heliopause's movement might even explain why Voyager 1 and 2 reached interstellar space 6 years apart, even though they followed similar trajectories. Scientists have observed the boundary creating shock waves and turbulence that ripple through both the solar system and interstellar space. This dynamic behavior suggests our solar system is more like a living organism than a static structure, constantly responding to galactic forces we're only beginning to understand. The implications are pretty profound. If our solar system's boundary is this unstable, what does that mean for the protection it provides against cosmic radiation?
Electronic confusion in the cosmic deep.
So, in May 2023, Voyager 1 began transmitting garbled, incoherent data instead of scientific measurements, as if the spacecraft was suffering from electronic dementia in the depths of space. 46 years into its mission, Voyager 1 experienced what NASA engineers described as electronic aphasia. The spacecraft's attitude articulation and control system started sending random, meaningless data instead of coherent status reports. From Earth's perspective, it honestly looked like Voyager 1 was losing its ability to communicate effectively, much like how a person with aphasia struggles to form coherent sentences. The mystery deepened when engineers realized that, despite the garbled communications, Voyager 1's radio signal remained strong and stable, which meant the spacecraft was still functioning normally. Its scientific instruments just kept operating without any awareness of the communication problem and the fault protection system, designed to put the spacecraft in safe mode during emergencies, never activated. After a lot of investigation, NASA discovered the problem. The control system had switched to a computer that had been dormant for years, basically trying to use obsolete hardware to process modern commands. The solution required sending precise instructions across 15 billion miles of space to reactivate the correct computer system. This incident really highlighted the incredible challenge of maintaining 1970s technology in the harsh environment of interstellar space, where cosmic radiation constantly bombards the spacecraft's electronic systems. Surviving the impossible, technology beyond its limits. Voyager 1's instruments should have frozen solid years ago when NASA turned off their heaters to save power, yet they continue functioning perfectly in temperatures that would destroy any other spacecraft. Honestly, the laws of physics suggest Voyager 1 should have died long ago. As the spacecraft's plutonium power source gradually decays, NASA has had to shut down non-essential systems to conserve energy. In 2019, engineers made the tough decision to turn off the heaters that keep the scientific instruments warm in the -270°F environment of space. This should have been a death sentence for the delicate electronics, yet all 5 instruments continue operating flawlessly. NASA engineers are genuinely puzzled by this phenomenon, unable to explain how 1970s technology survives in conditions that would instantly destroy modern spacecraft. The instruments operate in temperatures hundreds of degrees below their design specifications, totally defying every engineering principle. Some scientists theorize that the instruments generate just enough internal heat from their electronic operations to prevent complete freezing, while others suggest that decades of cosmic radiation exposure may have altered the materials in unexpected ways. The spacecraft's resilience has actually forced engineers to reconsider fundamental assumptions about electronics in extreme environments. This unexpected durability has extended Voyager 1's mission far beyond anyone's wildest expectations, allowing it to keep transmitting data from the interstellar frontier where no human technology has ever ventured.
The cosmic radiation bombardment.
Beyond our solar system's protective shield, Voyager 1 faces a constant barrage of cosmic radiation that's, wow, 3 times more intense than anything experienced within our cosmic neighborhood. Interstellar space has revealed itself to be a far more hostile environment than scientists ever anticipated. Once Voyager 1 crossed the heliopause, it encountered cosmic radiation levels 3 times higher than those within our solar system's protective bubble. This intense radiation, consists of high-energy particles accelerated by distant supernova, black holes, and other extreme cosmic phenomena. These particles constantly bombard the spacecraft, gradually degrading its electronic systems and creating cumulative damage that just builds over time. The radiation can actually flip individual bits in computer memory, causing small errors that accumulate into much larger problems. It's honestly like trying to maintain a complex machine while it's being continuously sandblasted by invisible particles traveling at nearly the speed of light. Despite this constant assault, Voyager 1 systems continue functioning through a combination of robust 1970s engineering and clever software workarounds developed by NASA's engineers. The spacecraft's experience provides crucial data about the radiation environment that future interstellar missions will face. Understanding these conditions is essential for designing spacecraft capable of surviving the journey to nearby star systems. Voyager 1 has become humanity's first radiation scout, mapping the dangerous terrain that lies between the stars and providing invaluable information for future deep space exploration.
Software updates across the cosmic void.
NASA engineers regularly send software updates to Voyager 1 across 15 billion miles of space, basically providing tech support to a computer system that's actually older than most of the engineers working on it. Maintaining Voyager 1 requires honestly some of the most challenging technical support in human history. The spacecraft operates with 1970s computer systems programmed in assembly language, a low-level programming code that directly controls hardware components. When problems pop up, NASA engineers have to write new software instructions and transmit them across the vast emptiness of space, where radio signals take over 22 hours just to reach the spacecraft. The engineers use a mix of assembly language and pseudocode to create efficient programs that won't overwhelm the spacecraft's limited 70-kilobyte memory. Each software update has to be perfect. There's really no chance for quick fixes or patches when your target computer is billions of miles away. These updates have solved critical problems throughout the mission, from reactivating backup systems to working around failing components. In one case, a software update saved Voyager 1 from potential disaster by activating fail-safe mechanisms when a hardware component failed. The process requires engineers to think like programmers from the 1970s, using techniques and limitations that modern computer scientists rarely ever encounter. This cosmic tech support is, honestly, one of the most impressive examples of long-distance troubleshooting ever attempted, keeping humanity's most distant ambassador operational out in the depths of interstellar space.
Revolutionary discoveries that changed everything.
Voyager 1's journey revealed that Jupiter has 3 delicate rings. Saturn's rings contain thousands of intricate braids, and volcanoes exist on moons we once thought were totally dead, completely revolutionizing our understanding of the outer solar system. Before Voyager 1's grand tour, our knowledge of the outer planets was limited to fuzzy telescope images and just basic orbital mechanics. The spacecraft's close encounters showed us a solar system far more complex and dynamic than anyone had imagined. Jupiter, which we thought was a calm gas giant, turned out to be a world of extremes, with hundreds of violent storms, glowing auroras, and 3 previously unknown rings that are honestly more intricate than fine jewelry. Saturn's rings, once considered simple and few in number, revealed themselves as thousands of individual ringlets with braided structures that seemed to defy the laws of physics. Most shocking of all was the discovery of active volcanoes on Jupiter's moon Io and nitrogen geysers on Neptune's moon Triton, erupting at temperatures just 40 degrees above absolute zero. These findings totally shattered the idea that volcanic activity was unique to Earth and the inner planets. Maybe most significantly, Voyager 1 identified potential habitats for life on Europa and Enceladus, moons harboring vast liquid oceans beneath their icy surfaces. These discoveries transformed our understanding of where life might exist in the universe, expanding the concept of habitable zones way beyond traditional planetary boundaries. The mission's revelations keep influencing space exploration today, inspiring missions to study these potentially life-bearing worlds in much greater detail.
The eternal journey into galactic immortality.
In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, carrying humanity's golden record message to any intelligent civilization that might find it. Voyager 1's scientific mission may end in the late 2020s when its power finally fails. But honestly, its journey through the galaxy is just beginning. The spacecraft will keep traveling through interstellar space for millions of years, eventually becoming an artifact of human civilization drifting among the stars. In about 300 years, it'll enter the Oort cloud, a spherical shell of comets surrounding our solar system. After 30,000 more years, it'll completely escape the sun's gravitational influence and start orbiting the center of the Milky Way galaxy alongside billions of stars. The golden record attached to Voyager 1 contains sounds, images, and greetings from Earth in 55 languages, serving as a cosmic message in a bottle for any intelligent beings who might encounter it. This record includes everything from Bach's music to whale songs, from mathematical formulas to images of human faces. The spacecraft has become humanity's first interstellar ambassador, carrying our story into the cosmic deep. Long after human civilization has evolved beyond recognition, Voyager 1 will continue its silent journey through the galaxy, a testament to human curiosity and our drive to explore the unknown. The mission represents more than scientific achievement. It really embodies humanity's eternal quest to understand our place in the universe and reach beyond the boundaries of our cosmic home. From mysterious cosmic humming to impossible electronic survival, Voyager 1's 47-year journey has shown that our universe is far stranger and more dynamic than we ever imagined. This brave little spacecraft keeps rewriting the textbooks of space science while carrying humanity's message to the stars. If you're fascinated by these incredible cosmic discoveries and want to explore more mind-bending space mysteries, go ahead and hit that like button, share your thoughts about Voyager's amazing journey in the comments, and subscribe to Sci and Y for more adventures into the unknown. Thanks for watching. Keep exploring the cosmos. On September 26, 2022, NASA achieved something truly unprecedented. They deliberately crashed a spacecraft into an asteroid at 6.6 kilometers per second and, get this, completely changed its orbit. The DART mission wasn't just about proving we could hit a space rock. No, it was humanity's first successful test of planetary defense technology. But what happened after the collision honestly shocked scientists and revealed truths about asteroids that nobody really expected. The aftermath of this cosmic collision is rewriting everything we thought we knew about protecting Earth from space threats. The journey to impact. NASA's Double Asteroid Redirection Test, or DART, began its historic journey on November 24, 2021, launching from Cape Canaveral Space Launch Complex 40 atop a SpaceX Falcon 9 rocket. The refrigerator-sized spacecraft traveled for nearly 10 months across 11 million kilometers of space to reach its target, a small asteroid moonlet called Dimorphos. The mission team, led by project scientist Dr. Nancy Chabot at the Johns Hopkins Applied Physics Laboratory, had meticulously planned every detail of this unprecedented experiment. Unlike previous space missions that aimed to study celestial objects, DART was designed with one purpose: to slam into Dimorphos and change its orbital path around the larger asteroid Didymos. The spacecraft carried advanced navigation systems that would allow it to autonomously guide itself to impact during the final 4 hours of flight, since the 11-minute communication delay with Earth made real-time control totally impossible. As DART approached its target, onboard cameras captured dramatic images of the asteroid growing larger and larger, marking humanity's first intentional collision with another world for planetary defense purposes. The perfect target. Dimorphos proved to be the ideal testing ground for this groundbreaking experiment, measuring approximately 160 meters in diameter and orbiting its larger companion Didymos every 11.9 hours. The binary asteroid system, located about 11 million kilometers from Earth at the time of impact, posed no threat to our planet, making it a safe target for this high-stakes test. Didymos, the larger asteroid measuring 780 meters across, served as the gravitational anchor for its smaller moonlet. Scientists chose this system because any change in Dimorphos's orbit could be precisely measured from Earth, using ground-based telescopes and radar systems. The asteroid pair was discovered in 1996, and had been extensively studied, providing researchers with detailed baseline measurements of their orbital characteristics. The proximity of the two asteroids meant that even a small change in Dimorphos's velocity would produce a measurable shift in its orbital period around Didymos. This binary system represented the perfect natural laboratory for testing kinetic impactor technology, close enough to Earth for accurate observation, large enough to produce detectable changes, yet far enough away to ensure complete safety for our planet throughout the experiment. The moment of impact. At exactly 23:14 UTC on September 26, 2022, DART slammed into Dimorphos at a closing speed of 6.14 kilometers per second, releasing kinetic energy equivalent to approximately 2.5 tons of TNT. The collision occurred with pinpoint accuracy, striking the asteroid's surface and instantly vaporizing the 610-kilogram spacecraft along with a portion of the asteroid's rocky material. Ground-based telescopes around the world captured the dramatic moment as a brilliant flash of light erupted from the impact site, followed by an expanding cloud of debris that grew brighter over several hours. The Hubble Space Telescope and James Webb Space Telescope immediately began observing the aftermath, documenting the evolution of the ejecta plume as it stretched across thousands of kilometers of space. Within minutes of impact, the debris cloud had expanded beyond Dimorphos itself, creating a spectacular tail of material that resembled a comet's tail stretching behind the asteroid. Amateur astronomers joined professional observatories in tracking the collision's effects, witnessing history as humanity demonstrated its ability to alter the path of a celestial object. The impact created seismic waves that rippled across Dimorphos' surface, potentially reshaping the asteroid's internal structure in ways that scientists are still working to understand.
Beyond all expectations.
The results of the DART impact exceeded every prediction and shattered the mission's success criteria. Instead of the minimum 73-second change in orbital period that would have declared the test successful, Dimorphos' orbit around Didymos shortened by an astounding 32 minutes. This dramatic change represented a 26-fold improvement over the mission's baseline requirements, proving that kinetic impactor technology was far more effective than scientists had dared to hope. The massive orbital change resulted not just from the direct momentum transfer of the spacecraft's impact, but from the unexpected efficiency of the momentum multiplication effect created by the ejected debris. As material blasted away from the impact site, it carried additional momentum in the opposite direction, acting like a natural rocket engine that amplified the deflection effect. Dr. Tom Statler, DART program scientist at NASA, described the results as a watershed moment for planetary defense and humanity's ability to influence our cosmic environment. The orbital change was so significant that it could be measured by small telescopes and even confirmed by radar observations from Arecibo Observatory and the Goldstone Deep Space Communications Complex. This level of deflection meant that if Dimorphos had been on a collision course with Earth, the impact would have shifted its trajectory by hundreds of thousands of kilometers.
The mysterious ejecta cloud.
The debris cloud created by DART's impact revealed secrets about asteroid composition that puzzled scientists worldwide. Instead of the uniform dust plume that computer models predicted, the ejecta displayed complex structures including multiple debris streams, spiral patterns, and irregular particle distributions that suggested Dimorphos had a far more complex internal structure than anticipated. Dr. Christina Thomas at Northern Arizona University, who led the observational campaign, noted that the debris cloud evolved in unexpected ways over the following weeks. Some particles were ejected at speeds exceeding 500 meters per second, while others moved much more slowly, creating distinct populations of material with different trajectories and behaviors. The cloud's asymmetric shape indicated that Dimorphos wasn't a solid uniform rock, but likely a rubble pile, a loose collection of smaller rocks and boulders held together by weak gravitational forces. High-resolution images from ground-based telescopes revealed that the ejecta contained both fine dust particles and larger chunks of material, some potentially meters in size. The debris cloud's brightness variations suggested that different types of material were being ejected from various depths within the asteroid, providing unprecedented insights into the internal layering and composition of small solar system bodies. Hera's investigative mission. Recognizing the need to understand DART's impact in detail, the European Space Agency launched the Hera mission in October 2024 to conduct a comprehensive post-impact investigation. This follow-up mission represents an unprecedented example of international cooperation in planetary defense, with Hera scheduled to arrive at the Didymos system in late 2026 to examine the crater left by DART's collision. The spacecraft carries advanced instruments including high-resolution cameras, thermal imagers, and radar subsystems designed to map both asteroids down to centimeter-scale resolution. Hera will measure the precise size and depth of DART's impact crater, analyze the composition of exposed subsurface material, and determine how the impact altered the internal structure of both Dimorphos and its parent asteroid Didymos. The mission will also deploy two small CubeSats called Juventus and Milani to conduct complementary investigations, including the first radar sounding of an asteroid's interior and detailed gravitational field mapping. Dr. Patrick Michel, Hera's principal investigator, emphasized that understanding the physical properties revealed by DART's impact is crucial for designing future deflection missions. The data collected by Hera will validate computer models used to predict deflection effectiveness and provide the foundation for operational planetary defense systems.
Unraveling asteroid mysteries.
The DART impact revealed that small asteroids like Dimorphos are far more complex than scientists previously understood, fundamentally changing how we think about these cosmic building blocks. Pre-impact models assumed asteroids were relatively simple objects with predictable responses to external forces, but the dramatic success of the deflection demonstrated that rubble pile asteroids behave more like fluid structures than solid rocks. Dr. Andy Rivkin at the Johns Hopkins Applied Physics Laboratory noted that the impact's efficiency suggested Dimorphos has very low internal cohesion, allowing the impact energy to propagate throughout the entire structure and eject material from multiple locations. The asteroid's surface appears to be covered in loose regolith, fine, rocky debris accumulated over millions of years, that was easily disturbed by the impact's shock waves. Spectroscopic observations of the ejecta revealed that Dimorphos contains ordinary chondrite minerals, similar to the most common meteorites found on Earth, but with unusual proportions that suggest a complex formation history. The impact also provided insights into how small asteroids respond to tidal forces from their parent bodies, with evidence suggesting that Dimorphos experiences ongoing surface changes due to its proximity to Didymos. These discoveries have profound implications for understanding asteroid evolution, the formation of binary systems, and the potential resources available on near-Earth asteroids for future space missions.
Complications for future defense.
While DART proved that kinetic impactors can deflect asteroids, the mission also revealed complications that will influence future planetary defense strategies. The unexpectedly large orbital change, while impressive, highlighted just how difficult it is to predict exactly how different asteroids will respond to impact. Dr. Nancy Chabot emphasized that the momentum multiplication factor, the ratio of total momentum change to the spacecraft's initial momentum, varied significantly from pre-impact predictions, reaching values between 2.2 and 4.9 depending on the measurement method. This variability means that future deflection missions will require detailed advanced characterization of target asteroids to predict their response accurately. The complex ejecta pattern suggested that asteroid internal structure, surface composition, and rotation state all influence deflection efficiency in ways that current models just don't fully capture. The discovery that small asteroids behave more like loosely bound rubble piles than solid objects means that deflection strategies must account for potentially dramatic differences in material properties between different asteroid types. Mission planners now recognize that successful planetary defense will require a library of deflection techniques tailored to specific asteroid characteristics, rather than a one-size-fits-all approach. The DART results also emphasize the importance of early detection and characterization, since deflection effectiveness depends critically on understanding an asteroid's physical properties years before any potential impact threat.
Global Planetary Defense Initiative.
The success of the DART mission has catalyzed unprecedented international cooperation in planetary defense, transforming what was once considered science fiction into practical space policy. NASA's Planetary Defense Coordination Office, established in 2016, now works closely with the European Space Agency, Japan's JAXA, and other international partners to develop comprehensive strategies for detecting and deflecting hazardous near-Earth objects. The United Nations Office for Outer Space Affairs has established new protocols for sharing asteroid tracking data and coordinating deflection missions, recognizing that planetary defense is a global responsibility requiring multinational collaboration. Ground-based survey telescopes like the Catalina Sky Survey in Arizona and the Linear program in New Mexico continue discovering new potentially hazardous asteroids at rates exceeding 1,000 per year, building a comprehensive catalog of objects that might someday threaten Earth. Space-based detection systems, including NASA's NEOWISE mission and the planned NEO Surveyor Telescope, will dramatically improve our ability to find and track smaller asteroids that ground-based systems might miss. The establishment of the International Asteroid Warning Network ensures that discovery data reaches decision-makers quickly enough to enable deflection missions if needed. These coordinated efforts represent humanity's first serious attempt to protect our planet from cosmic threats that have caused mass extinctions throughout Earth's history.
The future of planetary defense.
The DART mission's spectacular success has laid the foundation for humanity's first operational planetary defense system, but it also revealed how much we still need to learn about deflecting dangerous asteroids. Future missions will build on DART's legacy by testing different deflection techniques including gravity tractors, nuclear standoff detonations, and enhanced kinetic impactors designed for specific asteroid types and threat scenarios. NASA's follow-up missions are already in development, including concepts for multi-spacecraft deflection systems that could handle larger asteroids or provide backup capabilities for critical deflection attempts. The double asteroid redirection test proved that humanity possesses the technological capability to alter the course of celestial objects, marking our species' transition from passive observers of cosmic events to active participants in shaping our solar system's dynamics. Advanced computer simulations now incorporate DART's impact data to model deflection scenarios with unprecedented accuracy, enabling mission planners to design precise interventions for specific threat asteroids. The mission's success has also sparked development of rapid response deflection technologies that could be deployed on shorter timescales for newly discovered threats. Most importantly, DART demonstrated that international cooperation and scientific expertise can overcome seemingly impossible challenges, providing a template for tackling other global threats that require coordinated human action on planetary scales. So there you have it. NASA didn't just hit an asteroid, they revolutionized planetary defense and revealed that asteroids are far stranger than we imagined. Which discovery about the DART mission surprised you the most? Let me know in the comments below. If you enjoyed learning about humanity's first successful planetary defense test, make sure to like this video, share it with someone who loves real space breakthroughs, and don't forget to subscribe to Sci and Y for more incredible discoveries about our universe. Until next time, keep exploring the cosmos. A comet that shouldn't exist just forced the James Webb Space Telescope into emergency mode, and its data confirms a chemical nightmare breaking every rule in the book. The numbers are terrifying astronomers, pointing to something far stranger than a simple interstellar visitor. Is this object even natural, or is something else hurtling straight for us? The stakes only get higher from here. Let's explore this together. Emergency override, Webb's unprecedented response. What does it take to derail the most powerful space telescope ever built? On August 6, 2025, we found out. The James Webb Space Telescope slammed into emergency mode, pausing its entire science program for the first time in years. This wasn't a scheduled observation, it was a high-stakes director's discretionary time override. A procedure so rare it's only the fourth such event since launch in 2021. The target, an interstellar object designated 3Y Atlas, ground-based telescopes had just flagged it for accelerating in ways no one could explain, its spectrum flashing with unexpected metals. The call was authorized directly by the Space Telescope Science Institute director, Dr. Kenneth Sembach. The chain of command was short and swift, bypassing the usual committees that schedule Webb's time months in advance. The risk was immense. Webb's schedule is a precise ballet of fuel and orbits. A single, unplanned maneuver to observe a target for 5.3 hours could cost a week of other science. But the window to catch 3I Atlas was closing fast. Its trajectory was shifting by the hour. The command was uploaded and the telescope pivoted, its near-infrared spectrograph NIRSpec, locking onto a target that was rewriting astrophysics in real time. This wasn't a routine target of opportunity, it was a scramble to observe an object challenging our fundamental understanding of visitors from other star systems. Early activity beyond Jupiter's orbit. Here's where the story gets strange. Comets are supposed to be dormant deep freeze travelers. They wake up when they get close to the sun, typically inside Jupiter's orbit at 5 astronomical units. But 3I Atlas started showing activity far out, at 6 AU from the sun. That's nearly 900 million kilometers away, where temperatures hover around a frigid 110 Kelvin. The first hints came from the Pan-STAR survey in Hawaii, led by Dr. Ken Chambers, which noted a faint, persistent brightening. It wasn't just a flash, the object was waking up. Then the 8.1-meter Gemini South Telescope in Chile confirmed it. 3I Atlas was already sprouting a tail, a ghostly limb of gas stretching hundreds of thousands of kilometers. This is not how comets are supposed to behave. For comparison, 2I Borisov, discovered by amateur astronomer Gennady Borisov, began its activity much closer. The early outgassing of 3I Atlas suggested its engine wasn't the sublimation of water ice. Something far more volatile was driving this activity, a clear sign this visitor came from a place with a very different chemistry. It was the first clue that 3I Atlas was a messenger carrying a very strange message, one that began long before it should have. The carbon dioxide anomaly. The moment Webb's NARSPEC instrument locked on, the chemical picture came into focus, and it was a shock. The spectrum was overwhelmed by carbon dioxide. In the cold depths of space, CO2 ice turns to gas at much lower temperatures than water ice, explaining the early activity. But the sheer quantity was staggering, with a production rate exceeding 10 to the 28th molecules per second. Webb's data revealed a carbon dioxide to water ratio of 8:1. Let me put that in perspective. A typical comet from our solar system like Hale-Bopp has a CO2 to water ratio of about 20%, or 0.2 to 1. The interstellar comet 2I Borisov had a ratio of about 0.4 to 1. 3I Atlas was 20 times more CO2 rich than Borisov. As Dr. Neil Della Russo of Johns Hopkins APL, an expert in cometary composition, would note, this is completely unprecedented. The data was undeniable, with the telltale signature of CO2 at a wavelength of 4.26 microns burning bright and broad. Water was there, but only as a faint afterthought. This wasn't just a comet with extra CO2, it was a body fundamentally built differently, pointing to a birthplace where water might be a trace element, a type of protoplanetary disk our models barely account for. Nickel without iron, an impossible chemistry. But the carbon dioxide was just the appetizer. The main course was a chemical puzzle that, honestly, sent shockwaves through the astronomical community. Webb's spectrum showed clear, strong signatures of metallic nickel. At first, the team suspected an instrument artifact, but the lines held firm, confirmed by the Very Large Telescope's UVES spectrograph, operating at a resolving power of 80,000. The nickel was real, with a production rate of, get this, 10 to the 21st atoms per second at 3.8 AU. But here's the impossible part. There was no iron. In every celestial body ever studied, the cosmic abundance ratio is about 15 parts iron to 1 part nickel. 2I Borisov followed this rule. 3I Atlas shattered it. The data showed that nickel outnumbered iron by more than 40 to 1. Imagine finding a pure platinum nugget with no trace of other platinum group metals. That's the scale of this anomaly. Spectroscopists like Dr. Dennis Bodowitz, an expert on cometary composition, would be stunned. The nickel lines at 3415, 3524, and 3525 angstroms were unmistakable, but the spectrum was flat where iron should have been. One fringe theory suggests the formation of nickel carbonyl, a highly volatile molecule, but for this to happen without its iron equivalent defies all known astrochemistry. Trajectory anomalies and acceleration spikes. As the chemical data was being analyzed, the teams tracking the comet's path were facing their own bewildering problems. 3I Atlas was not following the clean, predictable arc of gravity. It was accelerating, showing a non-gravitational change in velocity of nearly 0.12 meters per second squared over just 72 hours. While comets do this, the force is usually gentle. The acceleration of 3I Atlas, however, wasn't smooth. The trajectory, tracked by the Minor Planet Center, showed tiny, sharp jumps. This recalled the mystery of Oumuamua, whose own non-gravitational acceleration was famously detailed in a 2018 paper by Marco Micheli. But this was different. For an object estimated to be 11 kilometers across, this is like watching a mountain suddenly shift course. The Pan-STARRS survey team ran every diagnostic, checking for software bugs or errors in their astrometry. The data was solid. The acceleration was real. It meant the forces acting on 3I Atlas were not just coming from the sun. Something else was at play, something internal, or something about its structure that allowed it to move in a way that defied our models, deepening the mystery and fueling speculation that this was no ordinary cosmic iceberg. The lighthouse effect, mechanical light curves. The weirdness didn't stop with its chemistry or its path. The way 3I Atlas reflected sunlight was just as puzzling. Photometric data from Gemini South and the TESS Space Telescope revealed a periodic brightening, a sharp pulse of light that repeated every 7.2 hours with almost mechanical regularity. It was like a lighthouse beam. A slow, gentle tumble is expected from an outgassing comet. But this was different. The brightness changed by over 2 magnitudes, a factor of 6, which is an extreme variation. The period was too constant. Dr. Karen Meach of the University of Hawaii, who led the team that characterized Oumuamua's wild tumble, would find this regularity highly unusual. For a normal comet, the spin should slow as it loses mass. But the 7.2-hour period remained locked in. Astronomers tried to model it as a spinning, elongated object, but the sharp rise and fall of the light curve didn't fit well. Other models suggested a hollow or even a sheet-like structure with sunlight glinting off a large, flat, reflective surface. The parallels to Oumuamua were impossible to ignore, but 3I Atlas was bigger, brighter, and its light curve was even more pronounced, more rhythmic, pushing the boundaries of what a natural object could be. Ancient sky metal, historical context. So, the idea of metal falling from the sky isn't new, it's really woven into our history. Around 3200 BCE, ancient Egyptians hammered beads from iron they couldn't possibly have smelted. Analysis of artifacts from the Giza tombs reveals the secret. The beads contain nearly 30% nickel. No terrestrial ore has that composition. The only source was a rare type of meteorite called an ataxite, and actually a similar story is found in Tutankhamun's tomb. Buried with him was a dagger with a blade of meteoritic iron containing 11% nickel and 0.6% cobalt, a composition detailed in a 2016 study in meteoritics and planetary science. This iron from heaven was incredibly rare. The Babylonians also watched the skies, and their cuneiform tablets speak of burning stones as omens. The Akkadian word for iron and bar comma is sometimes translated as sky metal. These cultures didn't understand the chemistry, but they knew this metal was different, special, and came from beyond their world. They understood that when the sky delivers something new, it can be both a wonder and a warning. Today, astronomers use powerful telescopes, but the core question remains, when an object arrives with a signature that defies explanation, what message is it bringing? Avi Loeb's challenge to consensus. As the data on 3I Atlas circulated, one voice cut through the cautious scientific debate. Harvard astrophysicist Avi Loeb. He had already made waves with his controversial hypothesis that Oumuamua could be an extraterrestrial artifact. Now, faced with 3I Atlas, he was even more direct. In a widely read blog post, he posed a blunt question: what natural process can produce a comet with pure nickel and no iron? He pointed out that separating these elements requires complex industrial processes. In the cosmos, it's considered impossible. Loeb connected the dots: the impossible chemistry, the erratic acceleration, the clockwork light curve. He argued that we must consider the possibility that we are looking at technology, a central mission of his Galileo project. His critics urged caution, but Loeb's position is that the anomalies themselves are the evidence. He contends that clinging to a natural origin explanation when the data contradicts it is unscientific. His challenge forced the conversation into the open, pushing the debate beyond academic journals and into the public square, demanding that the artificial hypothesis be considered on its own merits. Scientific community divided. The case of 3I Atlas split the astronomical community. On one side were scientists working to find a natural, if exotic, explanation. Dr. Alan Stern, principal investigator of the New Horizons mission, had previously proposed that Oumuamua could be a nitrogen iceberg from a Pluto-like exoplanet. Perhaps 3I Atlas was a carbon dioxide iceberg from a similar world. Others, like comet expert Dr. Matthew Knight, argued that the non-gravitational acceleration could still be explained by powerful localized jets. On the other side were those emboldened by Loeb, who argued that we had to take the artificial origin hypothesis seriously. They pointed out that a light sail, a thin, reflective sheet, could neatly explain both the sharp light curve and the acceleration. No one was claiming definitive proof, but the idea that 3I Atlas might be a probe, or a fragment of one, was no longer a fringe theory. It was being actively discussed. Peer-reviewed journals and online forums buzzed with debate as every new piece of data was scrutinized. The object was a cosmic Rorschach test, and what you saw depended on how willing you were to challenge fundamental assumptions about our place in the universe. NASA's High Anomaly Classification. Behind the scenes, the official response was one of cautious urgency. While public statements remained measured, NASA's Planetary Defense Coordination Office, led by Officer Lindley Johnson, quietly flagged 3-1 Atlas with a special designation High Anomaly. This classification is typically reserved for near-Earth objects whose behavior is unpredictable. But in this case, it was for an object whose very nature was in question. It wasn't a threat in terms of impact, but it was a scientific wildcard of the highest order. Internal risk assessments using systems like Sentry-2, usually focused on collision probabilities, were repurposed to track an enigma. The official line from NASA remained consistent: more data is needed. Extraordinary claims demand extraordinary evidence. Yet in private, even the most skeptical scientists admitted this object was unique. The data was being triple-checked and distributed to a wider network of researchers. But until a consensus emerges, 3I Atlas remains an official mystery, an object whose strange behavior has earned it a unique place in NASA's catalog of cosmic visitors. So, what is 3I Atlas? Is it a cosmic fluke, a messenger from a type of star system whose chemistry is alien to us? Or is it something more? The evidence is tantalizing and deeply unsettling. An object that moves on its own, shines with a mechanical rhythm, and is made of materials that shouldn't exist in nature. It could be the first definitive proof that we are not alone in the universe, a piece of technology from a civilization far beyond our own. For now, the answer hangs in the balance, locked in the data, awaiting the next observation that could finally tip the scales. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the mysteries of our cosmos. What do you think 3I Atlas is? Let us know in the comments below. Thank you for watching Sci and Why.